And we see where the market is going, what kind of discussions we have with customers. So this is my perspective. And I will describe to you what we call the digital twin framework. I will try to demystify it because it sounds like a little bit of a mystified concept. But again, it comes back. I will explain to how we do and relates to systems engineering. So one of the challenges, and these are general challenges for product development in general and system engineering in particular, is that the complexity of product is rising a lot. And this has to do a lot with the advancement of computing machinery, advancement of software, so the devices we design can do much more, and they do it mostly with lots of software. And this also brings lots of complexity to the system. So this is always creating more pressure. Designing a system 20 years ago, and I can give you the famous example of a car. A car, if you take a high-end car like a Daimler, a Mercedes, how many lines of code? Any guess? How much? How many lines of code in a Mercedes? Anyone has a guess?
100,000.
100 million. 100 million lines of code in a Mercedes, which is more than used to be in F-35. F-35 has 10 million. Now, I don't know F-22 and the next generation aircraft, but this gives you an example to the rise of complexity. And also, there's lots of software content that is coming. And with that complexity, there's another type of complexity, which is today in the markets we serve. We serve lots of customers. And we have to deal with lots of variants of the products that we build. We use the same platform, we try to use the same platform to sell to various customers, even inside the same country or in different countries. In the defense industry, I guess most of you are coming from defense here. I don't know if this is the right guess or not. Yeah. So in defense industry, you talk in terms of projects, customer projects. In automotive, it's a completely different business because they design the lines of the cars in advance. So they already know that they are going to have 10,000 variants of a car platform. This is the number, by the way. If you take the car platform, there are 10,000 variants, which means they manufacture 10,000 versions of the car. And this is also a challenge, how to engineer it effectively, but you also have the challenge, even if you are manufacturing a UAV and you have 50 customers for the UAV, it is also becoming a challenge how to do it effectively. There are some other pressures, regulations. Today we see more and more regulations. Before that, for example, in military, I did not see much regulation. Now I see more and more, for example, there is some enforcement of regulations like D178 on UAVs. I don't know if you have it, but in other countries we see that all kinds of safety critical regulations are coming also to defense. Needless to mention, in automotive or civil products, civil aviation, lots of regulations. And this creates lots of pressure in controlling development costs, controlling the time to market with all that complexity, and also maintaining quality. So there's always this type of pressure, and we see it both in military and non-military, or defense or non-defense. This always, we see, pushes our customers to look for solutions of how to deal with that complexity. And this is some information, why some motivation, why our customers want to improve product development. So first one is speed. I don't know how much this is relevant in defense. I did hear yesterday in the meeting I had here that there's, even in defense, there's very big pressure from the government to get the products way earlier than you would like to engineer them. But needless to mention, in civil markets, there is very high competition. And being there before the competitor is the name of the game. Right? Quality and higher performance products, this is another motivation. And then the third one is what I mentioned earlier, is customization of products. And this is also we see in both in civil and defense market, that there is a need to create more and more variants and highly specialized products based on the platforms that we have. Looking how technology is evolving around. So the technology we have today is obviously not the same technology that was there 20 years ago. We all see it every day, primarily around things like mobile phones and internet communication. And this also has impact in the environment that we operate in systems engineering. So there was a very big advancements in computing in two areas. And one area is cloud computing, which basically enables what we call elastic computing. So things that and I started my career as an embedded developer working on 8 bits, and we were counting bits, right? Today, the workloads that can be done using communication and communication with cloud system is huge. We can crunch huge amount of numbers. There's very high parallelism, and that also pushes what we call advanced analytics and cognitive analytics, artificial intelligence. This is the thing that pushed artificial intelligence. Because today, unlike 20 years ago, at some point artificial intelligence completely disappeared, because 20 or 30 years ago, artificial intelligence was based on searching trees. So it was good to play chess, but it was not good for vision, it was not good to understand natural language, and to do all kinds of things like brains can do. And now with the advancement of computing, GPUs, we can run huge statistical models and neural networks with huge number crunching, and essentially create a new generation of learning algorithms that are based on statistics. So everything you see today with autonomous cars, artificial vision, Google Translate, it's based on statistics. It's based on statistics and learning with huge databases. And this is what is all enabled by the advancement of computing, cloud computing, parallel computing, and this is why you see today AI is picking up. Obviously connectivity, you see it every day, software everywhere, and also sensors today are much cheaper. You know, in a cell phone, I don't remember how many, but there are something like 12 sensors, I think, on a cell phone, maybe more. And you can buy sensors today for very cheap and put them anywhere. And you can sense everything everywhere. This brought to this boom of what's called IoT. They say, okay, we have all those technologies, so instead of creating products that are 20 years ago were considered advanced, you know, shifting from completely mechanical products to products with electronics and some embedded software. Now we can create products that are connected back to the cloud. They are talking with the cloud. They are sending data all the time to the cloud. And this is the generation now that we are starting. In general, what we see customers, what they are trying to do with this technology is one thing is to create more innovative products. Create more innovative products, products that can do more functions because they can talk now to very high computing resources. And also they can do much stronger, much more powerful computing, even locally on the device itself. So this is one area. Another area that we see lots of demand in this is around operations. So today, everywhere we can sense things. So if we talk about factories or even large shopping centers, they spend lots of money on electricity, on energy, on basically managing all those spaces. So today with sensors, this is one example of how we can be more efficient, either in factories, in manufacturing, or in commercial. And there are many examples of how we can make operation more efficient. Going back to the area of systems engineering, so the role of system engineering, we start, and most of us think mostly in the design, specification, and engineering phase. But system engineering, if you look at INCOSE, you're supposed to think about the product life cycle, also throughout the operational phase and decommissioning, all the way up to decommissioning until the product finishes its life. So if we think about operations of products, we build aircrafts, we build all kinds of systems. Those systems are getting tired because there's mechanics, there's physics. It's not only software. Software never gets tired. But whenever we have hardware, products, they start to fail. And one of the big challenges is how, if we maintain a fleet of aircraft, or we maintain a fleet of cars, or we maintain a fleet of trains, how we make sure that we keep their utilization much higher, and we can eliminate unpredicted failures and all kinds of shutdowns. And this is also an area that sensing data is very useful. And this is the area of what we call predictive maintenance. Another area which is maybe more on the commercial side, and this is to better understand how products are used and engage with the customer that are using the products. But this is also useful in all domains, because with getting data from products, we can do analytics and understand much better how products are used, and then for the next generation of the products, we can simply design better products. So this is the concerns of life cycle, the way we think about it for connected products. So we start the product by some design of the product or engineering of the product, development, and then there is deployment of products, and then products go into operation. Operational phase, again, also as system engineers, we need to think about the maintainability of products. This is the important part also of system engineering. And then there is this loop that after the product goes into operation and maintenance, we start to get feedback from the product, and then we go to the next generation or new versions of the product, so we can use all the information that is coming from the products in operations and design better products. So we call it, this is called in the industry the IoT feedback loop. That rather than manufacturing products that we push to the customers and we don't really know exactly how they are being used and what's the profile of usage, what's the level of failures. Now we can have almost real-time understanding of how products are being used, and all kinds of engineering assumptions, we can get validation from the field. Now this is true today. If you buy a Daimler car, your car is connected to the Daimler data center. And Daimler engineers at every point of time can understand the full analytics of how their car are used, how they are used in cold countries, in hot countries, how different models are used, what's the level of all kind of parameters in the engines and so on. So we see it right there. But the evolution of this type of analytics, of sensor data, is also impacting, and we see it more and more also in more conservative area like military. So areas like predictive maintenance or doing analytics on flight data or any kind of even recorded data, the technologies are much more advanced today because we used to record flight data for many years or operational data for many years, but what we found that if you talk to organizations, they didn't know or they don't know what to do with the data. They don't have the right tools to understand what this data actually means. And today, because of all kinds of industries and the evolution of all those technologies, we have much better tools to get insights from data. Now, if we look at a product across an enterprise, so there are many functions that I already mentioned, and basically there are many silos that product lifecycle are going through. There is the design and system engineering area, there is the project office area, then there is manufacturing, then it goes into operations and maintenance functions and commissioning of product. So there's lots of product information all over the place, which is not really well connected. Each one of those, they are essentially what we call silos. The data that we know here, those guys understand, maybe those guys do not understand. They don't have access to the data. And insights that those guys have, those guys do not get, the engineers. So one of the big goals of product lifecycle is to be able to create some smart framework that with all this computing machinery, we can have very good understanding of how the product behaves and operates across its entire lifecycle. And one example why we want to do it is whenever we add a feature to a product, one of the basic questions we ask ourselves, and this is a system engineer, a classical system engineer role, is what is the impact of the change, right? We need to understand the impact of the change. Now, the impact of the change is not only in a software module that needs to be more complicated. The impact of the change can be how the product is maintained. The impact of the change may have to do with logistics, like how it impacts the logistics of the product, right? If we add a component that is not easy or is expensive to replace and so on. So all these kind of questions that system engineers need to understand are coming from all across the life cycle of the product. And we would like to give you an environment, and this is the goal of the industry when we say digital twin, that you can have this end-to-end vision of a product data. So this leads to the definition of digital twin. There are several definitions, and they are skewed by the company, by the strengths of the company that make up the definition. So there are companies that are stronger in mechanical CAD and simulation. So they will tell you the digital twin is mostly about being able to simulate the product and do mechanical simulation. And there are companies that are very strong in getting sensor data and do predictions. And they will tell you the digital twin is about getting the sensor data and tell you when the product is going to fail. And there are products that are stronger in systems engineering. For example, like we are focusing a lot on system engineering. So they tell you that digital twin is mostly the MBSC models, right? But the truth is that it is all of that. If you want to have the ultimate digital twin, you need to be able to have MBSC models and to have good simulation techniques, including physical simulations. And you need to be able to collect data from the product, and you need to be able to to do prediction about the product. It's all of that, but there is actually one definition I like from General Electric, which are, those are the guys that they know mostly how to collect data, but I can agree with their definition that this is a living model that drives business outcome, right? It needs to help you in the end, right? So what it is an information model that basically gives us all those insights and can answer all the necessary and support our decisions around the product. Engineering decisions, and also operational decisions that can save us money and help us create better products. So this is the high-level definition. And I'll give some example.
One thing to ask. What, upon my understanding, this is towards being used for understanding the end product before it's given life, right?
So this is what I said, it depends which company you ask.
Yeah.
If you ask a simulation company, this is what they will tell you. Because to understand how the product is used before it is coming to life, you need good simulation. But if you ask a company like GE, where they mostly collect data, they will tell you this is to sense the data from an operational product and being able to tell when the product is going to fail. And this is why we say here that digital twin has three entry points or three aspects, 3 point of view. One is the engineering, and this is what you meant. One is the manufacturing. Colleague before me mentioned Industry 4.0. So smart manufacturing is also part of it. And smart manufacturing is also about collecting data from the plant floor and make manufacturing more efficient. And the last area is operation. But usually you see lots of references, the common references are in engineering, and this is close to what you said. And you see lots of references, for example, if you look at GE, they will talk to you only about operation. They have this famous video when they have this power station, and there's this guy going on the stage, and he's using his voice and he asks the digital twin, when are you going to fail, right? Or when one of the turbines is expected to fail, and then the digital twin answers him using artificial intelligence and some voice, is going to fail in 2 weeks.
So from the point of view of the customer, I just want to understand what you say. Which level is enough to make them to raise a decision with which contractor or supplier or whatever to proceed with? Because now the customers are generally do not know at the bid stage which company would give them a better product.
Right.
They don't have a rational basis right now. They just go for it in terms of the contractual and pricing.
Right. So this is, and your system engineering, the most common point of view is the engineering point of view. Right. And this has a lot to do, and I'll talk about it, is to have good understanding and being able to predict the function of the product during engineering time. And that relates to MBSE and simulation and all kinds of technology. And also, as I mentioned earlier, is to be able to look at products that are already in field testing or already operating in the field. You know, we always have some aircraft that are already running on the field, and to be able to analyze the data that are coming from there as we are improving the product.
So the old product will serve into bringing the new product?
It's not even necessarily an old product, you know, because you have versions, right? You have, let's say you are selling an aircraft and initially you sold it to the Navy, and then you are selling the same aircraft to the Air Force, so you already have those aircraft flying, right? So these are some of the questions that we expect digital twin is orientation for engineering. So, for example, I mentioned the impact of change across the life cycle. Right? So essentially in engineering, what we are doing, it's rarely that we start with a clean sheet and we start to design a completely new imaginary product. We always take something and we apply a set of changes, and from something we have, we create a new product. This is engineering in reality. And to that, we have to understand the impact of what we are changing. Right? So understanding impact is a key mission for system engineers. Now, usually how they do it today, all kind of techniques for doing, asking all kind of people in the organization. There was always, the people with the white hair that have lots of experience. They can answer. I think it's going to be complicated there and complicated there. There are some spreadsheet type calculations and all kinds of stuff. And we would like this to be very precise. So if I'm saying I'm going to change something, I can see exactly where it is going to propagate. So that this is a classical example why I need this end-to-end traceability, end-to-end model, right? Or to doing a what-if, which is similar to that, right? What if I go this direction, going that direction? The other way around, identify a root cause. We started with deploy a product, maybe it's a product in customer accepted the first product, he is starting to use it, we start to see all kinds of problems. So identifying root cause for problems. By identifying root cause, we need to connect data that we get from the operation of the product, operational data, and take it all the way back to engineering. Even to simulation. If you want to identify root cause, if you get good data from a product in test, take it all the way back to your simulation, then the engineers that design the product can help you find what is the cause for the problem. What was wrong in the design. To do some of those things, we also use artificial intelligence because we are talking, as you can imagine, we are collecting lots of data, we have lots of engineering data, we have engineering data from other projects, and we can use also artificial intelligence, and I will show if I have time. I don't know how much time I have left. Okay. So we can use, some of the data that we have is unstructured. What do we mean by unstructured data? For example, if we look at the product, there are many logs or tickets that technicians opened against the product. So all those tickets are written in natural language. The technician wrote something, this is what I saw, this is how I fix. Right? And this is all written in English, in Turkish. So how we can leverage that? We need some artificial intelligence, or we call natural language understanding techniques, to harvest all the data that we have there. Another example, which will be even closer to you, requirements, right? Our requirements, which are very important, this is how the component supplier is going to supply the product. He's reading requirements. Maybe, I guess many of you are using those, even to write the requirements. Some of you are just writing them in Microsoft Word, maybe, some even in Excel. So how are our requirements written, even if you use those? They are written in natural language, right? And in order to understand the requirements and to get all kind of checking consistency or missing requirements, or finding if someone have developed something like that, you need to understand what is written in the requirement. So this is another example of unstructured data that we can use artificial intelligence to look into all this data that we have here and help us in carrying out engineering activities. What does it logically look like when we talk about digital twin? And this is pretty much agreed. So we have the different data sources. So big data source is engineering data. So we have all kind of functional models, could be physical models, could be requirements, right? Simulations, this is one type of data. And then we also have enterprise applications that have to do with logistics, purchasing, ERP, system manufacturing, execution systems, and they are also part of this picture. And then we also have the product during operation. So we already have products in testing, or we have products which is already in operation around the same system that we are working on improving. And this also provides lots of data that we can get from sensor. So the idea of a digital twin is the ability to have a central, what we call it, a knowledge base, to develop a knowledge base that basically associates and where we can ask or find relevant data for the engineering decision that we have to do. There's lots of discussions about how to build this knowledge base. Let me show you some example. This knowledge base is supposed to understand, collect the data from all those systems and be able to associate the data to create traceability between the data, right? To do end-to-end traceability, to see how a sensor that sends us data here is related to a value that I have in my system engineering model, right? They are talking about the same thing. They are talking a value of some system in the aircraft, and now I can see this real value inside the real operating aircraft. I need to be able to connect it.
How do you baseline the knowledge base then? You are collecting lots of information.
Yes.
Variance management, in that case. Are we baselining on the variance or the personal case when you do that?
It's a good question. We have a knowledge base that we can manage product configurations in the knowledge base, but I don't think, let's defer the question because I'm trying to understand the big concept, and you are already, I think you are a bit of an expert, and so it would be unfair that we start to discuss this question. Now, what I didn't mention here, which is also important, is how we consume the data. So we need to have good systems to be able to consume the data, to understand what is the data that we have there. So things like starting from dashboards, good dashboards that visualize the information, and also what we call intelligent experience. Intelligent experience, you see, if you look at digital twin in YouTube, you see that we can ask questions even in natural language, right? Which system is performing this function? We can ask in natural language, and then the twin comes back. Obviously, there's processing to understand what I said in English, to transform it into a query. The query goes into the knowledge base. There's an answer coming from the knowledge base, and then the answer is translated back, being put together in English, and then we do what we call a text-to-speech, and then there's a speaker that tells you the answer using voice. Okay? So this is the logical thinking behind it. Now, I'm going more down to what we have available today, at least from our standpoint. So, an entry point for what we call digital engineering, that at least integrates all the engineering disciplines that we have. And this is the platform, IBM platform, we call it platform called continuous engineering. So continuous engineering is a platform that can do several important functions and has an integration framework that can basically satisfy several principles. So one is the notion of digital thread. We can create traceability across all the systems that we have in engineering. We have technology to create traceability, and we create end-to-end traceability all the way from early requirements, going through MBSCs, through the simulations, through verification and validation, and then can go also to mechanical design, PLM, manufacturing, and so on. So we can, this is the idea, what's called digital thread, is the ability that if I'm looking at a requirement that I have as a system engineer can be translated to something in mechanical, something in electrical. It could be translated to something in manufacturing, right? So in order to understand all those associations, all those dependencies, we need to maintain what we call digital threads from that model. Another principle is continuous verification, and that goes back to what you said before. Continuous verification means that if I'm doing engineering, I would like to be able to verify as much as I can before the expensive verification. When is the expensive verification? That we all do verification.
Final testing.
Final testing, right, integration testing. So we put all kinds of stuff together, and then we go to expensive, I don't know if this is flight testing, all kind of expensive. Lab testing is also expensive because you have to reserve the lab. And if you are doing lots of stupid things, there's lots of pressure on the test lab. So we want to find problems as early as possible. It's called shift left. If we talk about the V cycle, it means we want to find things at the left side of the V. So the idea here is, on continuous verification, is to help you to verify the artifacts that you are developing, whether this is your requirements, written in English or in Turkish, or help you, and the primary mean to do verification of requirement is what? We discussed, I think it was discussed earlier. This is why we do MBSC. MBSC, the primary goal of MBSC is to basically create a specification which can be validated. Unlike if we write everything in English. In English we need artificial intelligence to validate. We're working on that, but this is really futuristic. But the most practical way to validate specifications is to build models. We can validate models. The next is to help us being agile, and I know there was some discussion about agile. And being agile is good. And when we say being agile, we don't mean that we develop a tank doing a scrum. You cannot develop a tank doing a scrum, right? Like you develop some IT software or some web application that you have 18 years old developers sitting in the room in the garage and doing the scrum. But being agile is good. Being agile means, it also means to be lean, that you can be very flexible, make the right decisions on the right time, find problems earlier. That's part of being agile. And avoid waste of time, doing lots of stuff, and then finding out very late that this stuff was the wrong stuff, and so on. We also have to be able to react to input we get from the customer. It happens a lot. I guess most of you are working in customer projects. Customer, many times, they change the requirements. New requirements are coming. So being agile means how quickly you can adjust your engineering, you can adjust your process to changing requirements, right? So when we say being agile, we give you infrastructure. We give you infrastructure that you can do things quickly, right? You can ask what if quickly. You can tell the customer very quick, if you want this change, it's going to cost you $200,000, right? Rather than building a committee that will do it in 6 months. Right? So this is what we mean by being agile. We don't mean that you build aircrafts doing a daily scrum in a small group. That's not going to work. The last area is reuse, and that goes back also to your question, is the whole business of configurations and being able to create different configurations, being able to support product lines. This is not a simple problem, especially if we do it across the product lifecycle. So if we take things like requirements and MBSC models, and then we have the engineering bombs and manufacturing bombs, everything has configurations and versions. And we have some nice technology, which is an open technology to do what we call federated configuration management, and to be able to do configuration management across the entire lifecycle. So far I was talking very abstract. This is the platform that we are talking about. So a set of functions across the V life cycle. On the left side, we have the creation, specifying the requirements, applying the system engineering activities, like the functional specification, and then the architecture, the allocation of function to architecture, and so on. And then going into discipline engineering. In our case, we don't do mechanical design in this platform. We integrate with systems that do mechanical design, but we can support in doing software component development. Also, verification and validation. It's very important to properly manage verification and validation and have it fully traced, which is this is the right side of the V with the left side of the V. So the most fundamental thing is that I need to understand every requirement that I have, how it is validated, and everything that I have in my validation, what requirements it comes to validate. This traceability is very fundamental. If you are doing regulatory processes, like safety critical, you are forced to do it. Everything needs to be the requirements. So this is the left side of the V. And then there are many activities that you have to do along the life cycle, and we have also capabilities to support things like end-to-end traceability, which I mentioned, the thread, things like change management, how we do a change, how we start a change, right? All needs to be digital and electronic, not with emails and you know, hallway discussions and stuff like that. It all needs to be data that I can see, I can track, I can see all the changes coming, which requirement the change is associated with, and so on. I mentioned the configuration management, which is the global configuration management, and things like planning, tracking, understanding where I am, understanding the KPIs of my projects, being able to calculate the KPIs, being able to calculate risk. So all these things are related to this mission to build what we call digital engineering. Meaning, in order to make all those things quickly and precise, I need everything to sit in an information model where I can find this information in a digital way. I don't have to find some Excel somewhere or find some guy who is today on vacation that he is the only one that knows how long this project is going to take. This all needs to be in one system that every role, based on what he needs to know, can find information. This is another picture of the system. And you can see different engineering capabilities with different, like requirements management, test management, VLV management, mechanical design, electronic design. They are all connected together using a protocol that we use, which is called Open Services for Lifecycle. Open Services for Lifecycle is a standard protocol, which is today monitored by a standards body called OASIS. And this is an open protocol to connect engineering tools. And it does two main things. One, it enables data across tools to be linked. So I can link, for example, data in MBSC model to some data in hardware in the loop testing. Or I can link some data from a logical model to a physical simulation model in Simulink. Right? I can link anything to anything. I can understand the association between all my systems. So this is one thing. The other thing that we need to do is we need to build a knowledge base that can answer all those questions, can give me the KPIs, can help me assess risk. And this is what you see here in the middle. This is the knowledge base. And we call it the lifecycle data graph. And this is also based on this protocol that every engineering tool that I'm using is contributing data to the knowledge base. Yes?
What does the JAS stand for?
Yeah, thank you for the question. So JAS, OSLC is an open protocol to implement integration. JAS is the IBM technology, the IBM technology to implement this. So you can implement OSLC compliant tool without JAS, which you can read the spec. But JAS is the core platform that we built in IBM to follow those principles.
Software production.
And there is another thing which I did not mention here, which is called Eclipse Leo. Eclipse Leo is a reference implementation that actually was contributed from JAS. That is an open source project. If you have, let's say, some ICD tool, many companies build interface control tools, some database with interfaces, and I think this is the tool that I found most homegrown type tools like that. So you want to connect it to that system, then you can go to Leo, and Leo will show you how to quickly you can connect your homegrown tool into this framework. So we provide you can get the specification, but then you can get also a reference implementation. Okay? How am I doing this time? Yeah. So let me, if there are more questions, I think this is the point where I can stop. If there are more questions, did it make sense? Do you think you know what digital twin is? No.
Yes. Is this basically something like a smart PLM tool?
It's an open. Let me tell you the difference. PLM tools, they have the belief that you can do your entire engineering by pushing all the data to one tool. Now, this system was created with the belief that you will always have. So you will never merge SAP with Dassault and Ovia. You will always have SAP and you have Dassault. You need a way to federate, to deal with federated data. So this is a philosophy how to deal with federated data while we can connect, associate, and reason about federated data. Okay. So we are a little bit insulted that you call this a PLM tool, because it's not the philosophy of PLM. Philosophy of PLM that everything needs to go in one database.
So it's like the link between a PLM tool and an MRP tool or any other knowledge site.
Yeah, in our case, it's an MBSC tool, or could be, or it's a project management. We have, I said, we have project management capability. So we're connecting project management capability with anything else, or test management, or you name it. Okay, and if you want to know more and see more, we have Karim here. It's unbelievable, he can demonstrate all of that and explain you how all of that actually works in real life. And maybe you will show some examples later on, right?
Yeah, if they're done.
Okay, thank you very much.